When we're talking about solubility product and the equilibrium of solutions, we need to think about a term called molar solubility, which is the concentration of a solute in a saturated solution. So once the solid has dissolved as much as it can be, whatever the concentration of the amount that dissolved is called the molar solubility. Simply put, when we do calculations with molar solubility, it's going to be the X that we put in our rice tables. So we're going to do a couple practice problems. We'll start off with the molar solubility of AgCl being given to us, and at a certain temperature, that's 1.33 times 10 to the minus 5. And if I know the molar solubility, I can calculate the Ksp for that equation. So we're going to start off by writing that equation. So the AgCl breaks apart into Ag plus and Cl minus. We write the equilibrium expression. Ksp is the concentration of Ag plus times the concentration of Cl minus. And we're going to set up our rice table. And the nice thing about Ksp rice tables is the solid doesn't show up. So I don't write anything underneath the solid. Now, at the beginning, when I'm starting to make a solution, I haven't yet started dissolving. So we're going to start off with 0 for the initial concentrations of the silver and the chloride. Because it's going to dissolve, some amount will break apart. So we're going to get some X Ag plus and some X Cl minus. Again, these X's are just one X because that's the coefficient in front of both of those species. And so at equilibrium, we're just going to get X. Now, that X is the molar solubility. So if I know that the X is the molar solubility, then I can take that number and plug it into my Ksp and do a quick solve. And I'll find that the Ksp for silver chloride is 1.77 times 10 to the minus 10. Now, I can also do this process backwards. So this is going to be that same problem, just worked out backwards. And now I'm giving you the equation, I'm giving you the Ksp. From the Ksp, I can define the molar solubility. Same thing, same process. We start with our rice table. We're going to not worry about the solid. We're going to start with 0 in both of my aqueous species. We're going to see a change proportionate to the coefficients, and so we'll get X and X. But this time, since I don't know the molar solubility, I'm trying to solve for that X, and I'm going to go back and just set up the problem like an algebra problem. I'm going to plug in X, plug in the Ksp that I know, and I'm just going to work it through. That's going to become X squared. I'm going to take the square root of both sides, and that'll leave me with an X of 1.33 times 10 to the minus 5. So I can do this process one way or the other. Doesn't really matter. Here's another problem. Let's see how you do with this next one. What is the solubility of PbI2 at 25 degrees Celsius if the Ksp is known to be 9.8 times 10 to the minus 9? Again, pause the video, take a moment, write out your rice table, get your answer, and see how you did. So I'm going to go through this pretty quickly. We're going to look at the equation. I do have to be careful because it's PbI2, so when it dissociates, it's going to produce 2 iodides, which means in my rice table, whenever I go in, I'm going to have 2X instead of just 1X. Again, I don't know what this is. I'm going to go in and plug in on the other side, write my Ksp. It's the lead times the iodide. The iodide is squared since I have 2 as my coefficient. I'm just going to plug in my equilibrium concentrations of X, go through the math, and that's going to simplify down to 4X cubed. I'm going to divide the 9.8 times 10 to the minus 9 by 4 and take the cubed root, and I'll get an answer of 1.3 times 10 to the minus 3. So hopefully that wasn't too bad, and you'll do all right with the practice.